Oh my gosh, here we go. It's 4:30. Calculus for the modern engineer time. Calculus with enthusiasm time. How about that? Let's do it. So we're working on how Laplace transforms can help us design feedback control systems, and our canonical controller will be a PD controller. You've probably heard the term PD. Stands for proportional derivative. So the story starts with you need to understand what a system is. And a system is you have an input and an output, and whatever transpires in between the input and the output, you can call that the system. If you're analyzing it in the time domain, whoops, come on. Bad connections. Yep, bad connections. Okay. For analyzing in the time domain with differential equations, you can include initial conditions. The transfer function method of Laplace transforms simplifies things a bit and assumes all initial conditions are zero. So this makes it very nice for computing the Laplace transform on the left-hand side because it is just as easy as computing it on the right-hand side. If all the initial conditions are zero, the Laplace transform of y triple dot is s cubed times y of s. And similarly for y double dot, s squared times y of s. So you do that, and you get the transfer function, which relates how y of s can be computed from u of s by multiplication by a rational function. And that rational function is called the transfer function. We can do the same for a state variable model, and for the segue that's worked out in the book, it's all done in detail, and for the ball-bot on project 3, you'll be deriving transfer functions from the state space model. If we have a transfer function, we can check stability in the sense of bounded input, bounded output. So bounded inputs like steps, sinusoids, etc. Do they or do they not always produce a bounded output? If they always produce a bounded output, the system is bibostable. And you can check that by looking at the poles of the transfer function, which are the roots of the denominator of the transfer function. The roots of the numerator are called zeros, and we'll get to them a little bit later, kind of late in the story, but they do come back. Now, in certain instances, you don't have to calculate the roots. You can just look at the coefficients of the polynomials that define the denominator, and you get a simplified stability test. It's necessary and sufficient condition. It's necessary and sufficient. And for a quadratic, it's all of the coefficients are positive. For cubic, it's a little bit more complicated, but not much. This one and this one have to be positive. And then A1 has to satisfy a special condition in relationship to A0 and A2. And in fact, similar formulas are known for 4th, 5th, 6th, 7th, 8th, etc. polynomials. The last thing we were working on is unity feedback systems. And so it's a feedback system or closed loop system because there's a loop here that's closed. This circle, we don't bother putting the summing in it. It's understood that whatever comes in with the sign that you place next to the signal, those are added up. So in this case, it's R plus minus y is defining E. So it's E is R minus Y. And so the error, the difference between what you want the output to do and what it's doing, is what's driving the system. There is a transfer function relating y to r, and we calculated that, and we got this g over 1 plus gs. And that's strictly equivalent to writing it as y of s equals, this is the transfer function of the closed loop system, and here's the reference. So it's just like when we had a normal, well, an open loop system. So there's no loop here. This is called an open loop system, whereas this one has a loop. Yay! That makes it a closed loop system. And then, wow, it looked initially, it was frightening to put a rational function over another rational function, but we realized that just by multiplying by the respective denominators, so we have 1 written down as d of s over d of s, and when you multiply that out, then it simplifies to something that's polynomial over polynomial. And in this particular example, we can tell that it's unstable by the simplified stability test, because this means s squared plus 0 times s, there's no s there, and minus plus a minus 1. So it fails a1 and a0 being positive. It's doubly unstable. It failed both conditions. No such thing as doubly unstable, but you get what I mean. We only needed one of those to be not positive for it to fail the Bibo stability condition. Whereas the closed loop, this is +1 and that's +1, so both of those, these equivalent coefficients are positive and it's Bibo stable. And I just wanted to emphasize this example wasn't from last time, but just so that you don't think feedback always stabilizes something. Here's something that's stable, got the same polynomial as here, and then I form the closed loop system, and look at the denominator. It's got 1, but a0 is negative, so it's unstable. So you have to be careful with feedback, and you know that feedback could be unstable because you've been in rooms with a microphone and a speaker, and we turn up the gain super high, and sometimes it will start resonating, right? And go squeak. That's instability, okay? That's instability. And then if you turn the gain down, like I just did, then it becomes more stable. Okay, so that's the background that we need to continue on PD control. Any questions on the summary material? Online, any questions? You excited to learn about proportional derivative controllers? Okay, you get to stay in the room. You were appropriately expressive, okay? That's really nice of you. Okay, so proportional derivative control and how to tune the parameters in it. And when we're done with today's lecture, you can basically do project 3. You'll have to read a few things in the textbook. But even a lot of that material is embedded into the Jupyter notebook. And I just want to emphasize the final exam, it stopped at computing Laplace transforms of signals, transfer functions, and an inverse Laplace transform. Okay, so just like, and you'll see that on the practice final exam. No feedback control on the final exam. Okay, so here's our first new thing for today. It's called a cascade control architecture. And it's the one we're going to adopt. Okay, so it's going to have a reference just like our previous one, plus, minus. What we're going to do differently is allow us to insert a rational function that we'll call a compensator. I'll come back and label that in a second. We're going to have a transfer function that represents the object we are trying to control. P is for plant, and I'll come back to that. It has an output, and it has a feedback loop. Okay, so it's cascade control because you are cascading the compensator. This is called a compensator. This is called the plant. Yes, plant, just like green thing in the house that you water, okay? But it's also the generic term for like a manufacturing facility. It's called a plant. So here, plant is used as the generic term for the system that is to be controlled. So the plant is fixed by you, the engineer. You designed it, you designed the Segway, you designed in Rob 311 the Ballbot, etc. So this is the reference, just like before. And then this is the output. And if you want to note the error, we can include that too. So the way block diagrams work, it's different than an electric circuit. Everything on here is carrying the same function, the same signal. So if I put something here and have it, what I'll be having is Y. So this is Y, this is Y. It's because they're all sharing a common wire, okay? Okay, so how does this relate to the feedback structure we had before? Well, you can see that G of S here, and we would have the same thing if we just treat that as a block. And so this is C of S, P of S. Whoops. Why did that happen? Okay, so we can apply the same formula that we had for a unity feedback, calculating the relationship between a reference signal and an output, as we had for a simple unity feedback system. What we've done here, though, is this is going to be a model of the Segway, and this is going to be our PD controller. So we've opened up this block so that we have a part that we design and a part that, who knows, maybe another company gave it to us, or a different part of our company designed it, etc. Okay. And so if we just write G of S equals C of S times P of S, we get the transfer function for the cascade system is, remember, it's G over 1 plus G. So it's C of S, P of S over 1 plus C of S, P of S. And the same techniques we had before for calculating the transfer function of the closed loop system applies here. Okay, so let's get our first controller. And it's going to be a proportional derivative which is always abbreviated as PD, proportional derivative, PD. So the compensator has a constant gain and then a KD times S. Okay, so why is it called a proportional derivative? Well, the KP term is proportional, but remember, S is the same thing as d by dt. So in the time domain, it really is differentiating whatever signal is coming into the compensator. So proportional derivative. Yeah, and I should have included gain here as well. So it's just a number, and we get to tune and twiddle these, and that's going to be fun. Okay, that's going to be fun. Now, I'm going to add one more signal name here. That's the input to the plant. So on the Segway, it's the torque at the motor that's attached to the wheels. It's a real physical system. The output of the Segway could be its lean angle or its speed. Okay, so then U of S is C of S times E of S from the block diagram. Okay, let's see if we believe that. Here's the error. It goes into the compensator, and that produces the torque, the commanded torque to the motors. And so we want to know how to tune the gains in this to make the plant have desirable behavior. And we don't know what that possibly could be yet, but we'll get there. So it's KP plus KDS times E of S. And if you prefer, in the time domain, that torque signal is KP plus KD d by dt times operating on the error signal. So it's got a proportional term on the error, and it's got another gain on the derivative of the error. And on Monday of next week, we'll delve more into the philosophy of why the derivative works from a philosophical point of view. For today, it's something that will allow us, as you'll see, to modify the terms in the denominator of a transfer function. Okay, so let's just see through an example, and then we can see if it answers the questions you have in your mind about what is the utility of feedback control with PD. So I'll do a plant, and so it's second order, numerator is just a constant 1, so it's a pretty simple plant. And you'll find out that it's pretty close to what the segue is, just different numbers, but it's the same structure. Now, here's A1, and it's not positive. Okay, so this is unstable. Can we stabilize it with a PD controller? Okay, so we select the only controller that we have in our library of controllers at this particular point, okay? We select a PD controller. So C of S is KP plus KD times S. So we're going to write down the PD controller enough times to where it's like, okay, I got it. You don't have to write it down again. As soon as you say PD, I think KP plus KD times S. That's a PD controller. Proportional plus derivative, and the derivative is S. So then Y of S over R of S is C of S, P of S over 1 plus C of S, P of S. So that's G over 1 plus G. G is the cascade combination of the compensator and the plant, or for you, the compensator and the plant. So is it stable? I can't tell by looking at that. Maybe you guys can because your minds are young and flexible. Maybe I'll put the PD terms in a different color just to make them stand out. There's the controller. Here's the plant. Over 1 plus KP plus KDS, then times 1 over okay, so we're going to multiply numerator and denominator by this term to clear the numerator and denominator, make it simple. And so we get KP plus KDS, because the plant just has 1 there. And then we get S squared plus, minus 2S. Then we have the compensator repeated. Now all I'm going to do is combine the terms. Okay, so I've got an S in here I can combine here, and I've got a proportional term that I can combine there, and there's no S squared term in the PD compensator. So this becomes S squared plus KD minus 2 times S plus 1 plus Kp. Okay, plant, PD controller, there's the closed loop system. So question for you. Find values for Kd and Kp such that the closed loop system is bibostable. Okay, somewhat annoying that my KD is, D is capital here and lowercase, but we'll overlook that, right? So what condition do I need on both of these coefficients for the system to be bibostable? Positive. And so if this is going to be positive, we need KD minus 2 to be bigger than 0, and we need 1 plus KP to be bigger than 0. So it's that simple. There's no trick here. KD minus 2 bigger than 0. So the derivative gain has to be at least something bigger than 2. 2.1 would do it, okay? And then 1 plus Kp should be bigger than 0. And that just says you can't make Kp too small. It can't be, you could make it a negative number, like negative a half, and it would still be stable, okay? So that's how the derivative controller, PD controller, can come in. You can see how it can adjust A0 to make it positive if the open loop system had had minus 2 here. Just like this, then we would have had Kp bigger than plus 2, okay? And then the derivative term allows us to adjust the S term in the denominator. Okay, so that's how that works. Okay, so there's a whole range of values. So, question. Right, there's an infinite number of values there. Which ones do we choose? Okay, if you don't have your laptop with you, as I posted on Piazza, but I didn't do it yesterday, I just posted it today, so that's kind of my fault. You got yours going?
I sent it to both of our.
Yep, and then maybe Daniel can team up with you. And Devin, is that a laptop or just an iPad? It is a laptop. Oh, you got both there. You're always good. And you guys got your laptops? Okay, so go to Vocarium. And go to Demo 3. So it's Chapter 10, Demos. Don't log me out and log me back in. Okay, that'll give you guys time to get logged in. Chapter 10, Demos. Yes. Struggling under all of the... Come on. Okay, so you can read what's in, there we go, finally. Demo 2, that was before. Demo 3. Okay, so we're just going to take an open loop system. So once we calculated the closed loop transfer function, it was a gain over s squared plus something times s plus a constant, okay? So it was a second order transfer function with just a constant in the numerator. So what I want you to do is to adjust the coefficients in the transfer function such that when I apply a step input, the output looks like this. And you're going to struggle, okay? But take a few minutes. You need to run cell 7. It defines two functions. And then the coefficients you are going to adjust are B0, which is in the numerator. You can see in line 13, the second order transfer function has a constant in the numerator, and then it's got A1 and A0, just like we were talking about. And A1 and A0 are positive on this initial thing, okay? I don't remember what numbers I put in there and why, okay? So run it and then tune it. There we go. Doesn't look very close to this, okay? So this, we gave a command for the output to become 1, and it took about 3 seconds, 4 seconds for it to get there and stay there. Okay, so play with A0 and A1. You can leave B0 like it is if you want. And just play for a couple minutes and see if you can get anywhere close to something like this. I'll keep this up while you're playing with it. Did you get it?
I'll help the people in the chat.
Yeah. Okay, guys. Get it going. Okay, so once you've run it once, you can just change those numbers and hit run, and it will instantly produce your plot. Yeah, so it's chapter 10 demos, and we're on demo 3. And if you don't get to this one in time, it's okay. You've saved yourself a world of frustration, okay? This one, that's what this whole problem is about, so that the next problem, you go like, oh, that was pretty powerful information. Thank you for sharing that, Professor Grizzle. Okay, so that's the purpose of this one. You guys getting anything online? You getting anything close to what I've got? At least it doesn't oscillate for 2 days or something. Chapter 10. Oh, it's like cell 7 and 8. Mm-hmm. Well, you're in part 1. You need to be in the demo. Yeah, the demos. Yeah, that's why. Oh, that's pretty good. That's a winner, okay? That was so close. You just got started late, right? Yeah. Kernel's still connecting. I love those kernels just connecting and connecting.
There's no assignment.
No, it's no, but you go to pages, code from the textbook,
I see.
chapter 10. Yep.
I'm running cells on.
You're able to run. You can't get any, you don't have any decent results.
Yeah, not yet. It took a second for
You get anything?
Still running.
It's still running. Okay, well, let me check over here and then guys get anything? That's great. You must be proud. Hey, that looks almost identical to it. Did you cheat and go down and get my parameters and put them in there? No? You actually chose them yourself?
Yeah.
How'd you do it?
2 point by 2 point by 2 point.
You just guessed, right?
Yeah.
Okay. Okay, so I see several of you got something that is like amazingly close. And if you had played this joke on me, with what you know, I think I would have flipped out, okay? So bravo, bravo. Okay. Okay, so let's go back. Let's go back and get some more information. Okay, so here's kind of a typical step response. So it's called a step response when you put a unit step in and then you look at the output. Why do people like to use unit steps when they're tuning a control system? It's because everything is quiescent, nothing's happening, and then boom. So you're hitting the system, and anything that is slightly oscillatory, you're exciting it, okay? So if you've got some things that want to oscillate, they've got the energy with that boom, okay? It goes boom. That's a unit step. So some parameters that people look at. Y infinity is the steady state value. So look at your signals. Maybe if you didn't have the time set long enough, well, I didn't have the time long enough for the parameters you have, yours is still oscillating. But if the system is stable, it will go to a constant value. That's Y infinity. We define what's called a settling time by look at the steady state value, go 5% up and 5% down. How long does it take the response to get within that plus minus 5% bracket and stay there? So here, it got within it, but it didn't stay. It got back within it, but it didn't stay. Now it got within it, and it stayed in forever. So this point here, from here to here, that's called the 5% settling time. So it's saying how quickly is your system able to get close enough to the steady state value to be useful to you. And if 5% is not accurate enough for you, people also look at 2% settling times. We're just going to stick with 5%, okay? And if you want to do the 0.1% settling time, more power to you. You can do all of those, okay? So that's just a performance metric. It's giving a speed of response, because here the response is not so useful. Now it's pretty accurate to the steady state value. The other thing we look at is the percent overshoot. So that's Y max minus Y infinity normalized by Y infinity and then times 100%. So this is on your handout, the key performance things. So I'm just going to paste them in. Underdamped key. Okay, so percent overshoot, Y max minus the steady state value normalized by the steady state value times 100%. So that quantity is independent of units. If Y is gallons per second or meters per second or meters, it's the same units in the numerator and denominator, they cancel, so it's unitless. And then the settling time we typically do in seconds, but if you have a really slow process, you might want to use hours. And so it's how long it takes to get within plus minus 5% of the steady state value and stay there. So it's the smallest t such that you get within this band and you're there for all future values. Okay? Okay, so now let me define, it's on your handout. This is called a standard second order system. Standard second order. What makes it standard? Well, if you plug in S equals 0, so these things go away, you have omega n squared over omega n squared, and you get 1. So it's normalized to 1. That's part of the word standard. The other thing is we've written the coefficients in a special way. So this number here, zeta, is called the damping ratio. Okay. If there is no damping, so if you just have a mass and a spring and you release it, it just oscillates, but there's a natural frequency of oscillation. Okay? So you'd have S squared plus omega n squared equals 0, and so the roots are plus or minus I times omega n. And we know that I omega n in the exponential gives cosine and sine at that frequency. So omega n is called the undamped, so you remove the damping, undamped natural frequency. Okay, so here's the beauty. Whoa. Come on. You can breathe while I go crazy looking for. It's not there. Oh, come on. No. I am sad. Okay, so you're forced to look at my drawing. Okay, so this is going to be 1, y infinity. And if the system is really heavily damped, you get something like this. It's very lightly damped. You get things like this. Okay, so there's a better picture in the book. And all of these curves are parameterized, so this would be like zeta equals 2. This one, zeta equals 0.7. This one, damping ratio 0.3, for example. Okay, so the curve I wanted is actually on the handout, but it's not in my little repository of graphics, okay? So here you can see all the different curves, and the values of the damping coefficients are in the lower left corner. So if you turn to the side of the page that has pre-compensator and things, it's got a whole bunch of step responses on the left, okay? And then I'm going to hope this next one is there. No way. I can't be this ill prepared. I had them all. Oh, this will do it. Okay, so this is also on your handout. So if you know the value of overshoot that you want, so say 5%, 0.7, 15%, damping ratio 0.5, you can just, as part of your design, fix a desired damping ratio. We typically use this one. And then once you know your damping ratio and you know the undamped, and you choose an undamped natural frequency, you have a settling time, but that means you can just solve for the undamped natural frequency. So you have TS is 3 over zeta omega n, and this is the 5% settling time. The omega n you want is just 3 over zeta times TS. Okay, so that's pretty important. So as part of your design, you can pick the speed of response, which is the settling time, and then how much overshoot there is. Now, why would you want some overshoot? You would say, I want none. Well, yeah, here's one. And it's going to take about 4 days to get to the steady state value, okay? So imagine you've got a spring, and you got sandpaper, and you threw some extra sand, and you put some glue on it for friction, and then you let that go, and it's going to take so long to finally settle out, okay? It's not going to oscillate. So you want the damping ratio to be small enough that you get a fast response, but not so small that you get tons of oscillation and it takes a long time to actually die out. And I'm sorry that I don't have this curve up on the screen, but there's a poor man's version of it, a Grizzle's version of it, okay? So I'll get this going, and you can still take a break, but those of you who want can start playing with it. Okay. Do this problem 3 again, but this time set the settling time to 3 seconds. So TS is 3 seconds. and the damping ratio equal to 0.7. So go in here, figure out that this one is omega n squared, this is 2 zeta omega n, adjust B0 so that it's equal to omega n squared. So set your TS equals 3, your zeta equals 0.7, and then solve for the values here to turn this into a standard second order system. So look at your formula for the standard second order system, do the B0, A0, A1s, and then see how close to this you get, okay? And it's just one shot is the point here. It's a single shot. You're not guessing anymore. So we'll start our break, and we'll come back at our break at 5:30, so you guys can take some time and then start playing with the numbers. We're just talking. We're not doing anything serious. So on the segue, when we get to it, we'll compute how long it takes to rotate 90 degrees. So your speed of response better be quicker than that, okay? If it's trying to pick you back up off the ground, it's all over, okay? So that's where the physics comes in. It's going to be a couple milliseconds. You're going like, whoa, okay, got it. Yeah, and then how much oscillation? Well, you can see what you want is your analytical stuff on your mathematical design. When you put it on the model, that it gets you close, and then you can just tune a little bit by hand. You run an experiment, you change one knob, you run another experiment, you put it back because it got worse, and you go the other way. Okay, so you hand tune at the very end. Because you may say, oh, I need a damping ratio of this, but if your joint has friction in it already, and that's not in your model, then you don't need to add that extra friction. That's what the damping, the PD is doing. It's adding in the damping part. Okay, so if it's the robot joint. Now, if you already have that friction modeled well, then you can do it more closely. So that's what's going on. Okay, people online, were you able to get a step response that looks like the required one? Yeah, you guys get it? No? One of you? Anybody over here? Oh.
I was actually messing with the
No, I think you guys just copied my figure and you put it there, okay? Yeah.
No, I actually was messing with the KDK area.
Yes, we've got things. We need to calculate omega n, and I said that was 3 times, let's see, TS is 3 over zeta omega n, so it's 3 divided by TS times zeta. Okay, and this one needs to be omega n squared.
How does 3TS correlate to 5% settling time again?
TS doesn't, it's the damping ratio that does. Yeah, TS is the settling time, so how long it takes. And then this one is also omega n squared, and then this is 2 times zeta times omega n. Wow. I'm able to manipulate that formula in my head. Yay. Okay. So now, let's do demo 4. Because this is what we really want to do. We want to tune a PD controller. Okay, so I'm giving you the parameters of the plant. The plant has a gain, K0, It has S squared plus A1S plus A0. It's unstable, right? I'm really nasty. The plant is unstable. We have a PD controller here. Okay. And just as we did before, where there was a 1, instead of being a 1, there's a K0, and there were numbers. There's now an A1 and an A0. So we get the transfer function of the closed loop. Okay, so you guys understand that I would choose KD to make this number positive and KP to make this number positive so that the system is stable. Okay? Now, if I take and rewrite this in that second order form, I can solve for KP and KD. It's just algebra, okay? So that same one-shot solution, if we believe this is the model, a world-leading authority on crazy parameters gave us these. That was me, okay? Said, this is our plant. We're using PD control. And so now your job in the next cell is to design the coefficients here so that the closed loop system has approximately 5% overshoot and a 5% settling time of 3 seconds. So these are the same specs you had when you just had a second order system. So your work starts here. So I put in the plant coefficient, I put in the plant. Here's the PD controller. Here's the forward path transfer function. This is a command in the control package for Julia that will compute the closed loop for us, so we don't have to do the CP over 1 plus CP. We just specify the forward path, and the feedback path is a 1. And then we'll do the step response, okay? So you guys need to fill in here, and your goal is the same specs that we had before. And, oh, Jason, you didn't get it. You have questions for Max or me?
Or just,
Huh?
it's like A naught, where you showed them about.
Okay. Oh, just following along. Okay. Good. I wasn't sampling adequately quickly, Jason, to follow the conversation that I was having. I apologize for that. So, yeah.
Can you scroll back up for a second?
On this cell or this one?
The previous cell, like the one where we were coding a second ago.
Yeah, here?
One more up, I think.
This?
Yeah, I was trying to remember how you were defining
Whoops.
zeta and W.
Yeah, so this is what you want for omega n. You can still use that, okay? You want to write it down, or you already had it in your thing?
It was mostly already in my thing, so I just changed one number.
Yeah. Okay. And then you see that, okay, the derivative term changes what multiplies s, and the proportional term changes the constant part of the denominator. So we are shaping the poles by adjusting the gains. Okay? But we're doing it a little bit indirectly, in that we're writing the poles in terms of a damping ratio and an undamped natural frequency. That makes it easier to understand from this. Okay? And so you've got the plant, you need to define KP and KD, and notice that it's K little p and K little d. Okay. It just looks better in code. When it's typeset, K sub p, the big P is easier to read in LaTeX. Now, spoiler alert, you're going to come close, but it's not going to work perfectly. And we're going to understand why. And then all of a sudden, when you get to the segue and you have multiple blocks to design, they're all motivated. You'll understand what's going on. Okay, anybody got any preliminaries to show me?
Oh,
You copied down the KP, KD, that's good, yep. Mm-hmm.
but the results I'm getting.
Yep, son of a gun. Yeah, that's a spoiler alert. Yeah, you can copy those formulas right there. You can just click on it and copy them. Or you can just quickly write them in. Yeah.
Oh, I just looked at them. I looked at them on the cell phone. Just typed them out.
Getting anything to work?
I just copy the KP value.
Yeah. Okay, so you want to compute those in a little bit better way. Yeah, that's correct. Unfortunately, it's not what we want. It's correct, but it's not what we want, okay? You haven't done anything wrong, and it's not right. It sucks, huh? So there's something more going on here, and we need to understand what that is. Okay, so I hope some of the people online have it. I'm going to steal my code. You guys can steal it too, okay? It's like cell 13 or something. Your work starts here. Okay, there's my work. So I put in the settling time for the percent overshoot, use 0.7 for zeta. Okay. Use the settling time formula to get my undamped natural frequency, and then use the formulas to get the KP and KD. There's the controller, there's the forward path, and the closed loop is forward path, CP, and the feedback path 1. And so it's kind of close. So it's settling in about 3 seconds. Okay, so that part worked out. Here's the steady state, you know. It's not 1, it's 1.5. And I've computed the percent overshoot, but you can look at it and see that this is about 1.7, 1.75 or something. And when you compute the percent overshoot, it's 21. And we were going for what? 5%. Huh. How could we mess up? Right? How can we possibly mess this up? There's the denominator of a standard second order system, and we perfectly did it. I know you guys did. Okay? But look, is this omega n squared up here? This is the numerator. That standard second order system had omega n squared. This coefficient repeated here. And the answer is no. So, Okay, so here's what the PD controller did. So we have something that looks like this. And, let me just put in the standard thing down here. There's another gain, but we'll worry about that in a second. But this is what our closed loop system is, approximately, okay? I'm leaving out a few terms, but the key thing is, oh yeah, there's the PD thing in the forward path. And the forward path numerator always comes through. So this, I'm going to write as KD times S plus KP over KD. Doesn't change anything. Okay, so if I have my standard second order guy, in fact, let me put an omega n squared up here just so that I have the second order thing. And so this thing, when we do the step response, it basically looks like this, 1 minus, and then there's an e to the at, there's a sine omega t plus theta. That's derived in the textbook, but you can just compute, you put a 1 over s on this guy and you compute the output, it has that form. Now what's the problem up here is that G closed loop with the PD controller equals a gain times, I'm going to call it S plus a 0. Remember those zeros, those things that are in the numerator? Okay. Okay, so Z was KP over KD. The PD controller puts a 0 in the numerator. Okay, so the 0's at minus Z. So what does that do to the output? So why closed loop? Well, there's this term, whoops, I left off my omega n squared. Okay. So it's KD S plus Z times my previous y of t, and that S is a d by dt. Okay, so if the gain wasn't omega n squared, my output is not going to be exactly 1. That's coming from that KD. Okay, so that's, and then it's scaled by Z. But then the worst thing is we end up with KD d by dt of y of t. And so y of t is the standard second order. So it's got zeta equals 0.7, omega n equals whatever we needed to, it has the settling time equals to 3. Okay? But look what happens here is we take d by dt of one minus e to the at sine omega t plus theta. And then that derivative is what? Minus a e to the minus at sine omega t plus theta. And then we've got the second term on that, which is e to the at. We get an omega from the chain rule. Okay, so we have these two extra terms in the output that come from the zero of the PD controller being in the forward path. And so the output is no longer a standard second order system. It's the standard second order system plus this term, and that's causing the offset and the additional oscillations. Okay, so this is the additional oscillations. Okay, so that's from, darn it, you know, the PD controller, it let us tune the poles, but it threw a zero at us. And that's the problem. So let me do a pole zero plot. So these are our second order poles. And there's the zero. So if we could remove the effect of the zero, it would no longer be causing us any problems. So is there a way to remove this zero? And the answer is yes. So can we remove the deleterious effects of the zero added by the PD controller? Okay. If I just had a transfer function and I had an s plus z on top and I had an s plus z on the bottom, what would we do? We would go cancel, cancel, okay? We've got the s plus z on the top. Can we put an s plus z on the bottom to cancel it? And so the bottom line we can cancel a stable zero. Stable zero, this is the left half plane. So poles in the left half plane are stable. They have negative real parts. We can cancel a stable zero with a stable pole. So we never, ever, ever try to cancel an unstable pole. And the idea is we're going to set a pole on top of the zero so that it cancels. Now, how do you do that? Okay. You're here. Don't tell me you closed. No, you didn't. Yay. Okay. So here's how we do it. The PD compensator puts a 0 in C of S, and that comes through. We're going to put a pole before it, before the reference command, and cancel that 0. Okay, so you've got this on your handout as a cheat sheet when you're doing the work, okay? We can do another thing as well. So if there's an S plus Z here, we can put a 1 over S plus Z here. Another thing we can do is we can add an additional gain in here and take care of that steady state error. Because look, we commanded the output to be 1 and it's settled at 1.5. That's not good. Okay, so in the text, so the error, the true error, this is the reference command. So this is going to be 0 degrees lean angle for the segue, or it's going to be 1 meter per second for the speed. This is the measured quantity. The error is no longer this one because the command has been filtered, and so this is something else. It's whatever it takes to go into the controller such that what comes out is a torque that we can apply to the plant and get good things to happen. You can calculate that the steady state error from R to Y, the error, is given by this formula. 1 plus 1 minus what's called the DC gain. When you take a transfer function and you plug in 0, okay, the imaginary part of that is 0, and that's the frequency, so that's why it's called DC gain. You can do the same for the compensator and the plant. And then you can just solve this to make the steady state error equal to 0. So you want to set the numerator equal to 0. And so we're going to write this pre-compensator as a gain times Z over S plus Z, where Z is coming from the PD controller. So KD times 1 plus KP divided by KD. So that defines Z. We're going to cancel that with this pre-compensator. And then, in addition, we're going to choose the gain such that we get 0 steady state error. And voila. Okay, so that's what we get without the pre-compensator. And now we've got it, okay? Now we've got exactly the 5% overshoot, and the settling time is, it's about 3 seconds, okay? So the idea is, as I was showing here, oh, come on. Is with the precompensator, we're putting a pole that when it's multiplied, it cancels the 0 that's from the PD controller. So this is called, so here is our cascade controller. There's the plant. There's the PD controller. And then to recover the properties that we wanted from the second order system, we need to attenuate the effect of the extra differentiation caused by the 0 in the PD controller. And we cancel that with a stable pole. Okay, so it'll take you a little bit to go through this, but the compensator, the precompensator is really simple. It's a gain, and then this number Z comes from the KP over KD. It comes directly from the 0 of the precompensator. And there it is. And so I can build the precompensator. I've got my PD controller that I had before. Bad, well, it's not terrible, okay? But now I add in the precompensator before the closed loop system, and then I get exactly what I want. Is that cool? It's surprising, and it's powerful, okay? And the ideas for doing this comes from the Laplace transform. If we were just looking at the differential equations, it would be really hard to know what to put, that you could put an additional, using electrical engineering terminology, a filter. This is filtering the command. It's actually a low-pass filter, creating an artificial command, a filtered reference command, that artificial command then causes the closed-loop system to behave like an ideal standard second-order system. Are you stunned? Does it seem too easy? Questions? No? Anybody online like to ask a penetrating question? Okay, so I did all the algebra for us. No? Okay, well then you're going to be turned loose on the ball bot in project 3. In the textbook, it does the segue and it parallels 100% the ball bot. So there's a couple of missing ingredients. So here's some missing ingredients. So the first one is that the segue is a nonlinear model. I'm going to write it first. I'm just going to put the torque in like this, okay? So you'll see where they, now let me put this as a B, like this. Okay, so here X, it's the lean angle of the segue, it's the rotation angle of the wheels, it's the velocity of the rotation of the upper body, the lean angle, and the speed of the wheels. So that's the state, but it's nonlinear. it has an equilibrium when the lean angle is 0. You can set the wheel angle to anything you want, 0, and then the velocities are 0. Okay? So that's an equilibrium. At the equilibrium, the differential equation, the right-hand side, this part is 0, and if we set the motor torque equal to 0, then nothing's happening. Okay? All of our methods have been for linear models. Well, if we perturb away from the equilibrium, we know from calculus that this can be written. Okay, so that's the linearization of that. That's the linearization. At the equilibrium, this is 0. And this is just a constant matrix. It's 4 by 4. And you can derive then that we have a linear approximation of the nonlinear model. So this is a linear approximation of the differential equation. How hard is it to do? Not at all. For the nonlinearity, we can just use forward diff and the Jacobian to calculate this. This we get from either NL solve, but for the physics of the Segway, it's very easy. And for the ball bot, it's very easy. The equilibrium is when everything is upright, just like an inverted pendulum. And so we can calculate this linearized model very easily. Okay? Segway also comes from the robot equations. So here the generalized position is just going to be the lean angle of the Segway and the rotation of the wheel. Okay, so this is a Segway. See the platform where you stand? You got to shrink a little bit, okay? So this is measured by an IMU that's on the Segway. The same for the ball bot in Rob 311. There's an IMU right here. Now, how is the angle of the wheel measured? They put an encoder on the axis where the motor is, okay? So that encoder is mounted to the motor, which is mounted to the base, okay, where you're standing. And so it's measuring rotation relative to the body of the Segway. It's relative. Now, Where do you want to call 0 of the wheel? Here? Here? It doesn't matter, right? There, I set it down, that's 0. It's kind of inconvenient for you guys, so we're going to take it as 0. When the encoder is lined up with the torso of the segue, we'll call that 0. Okay? So that's the angles. And then it has the robot equations. And remember, that's the external forces like torques, external motor torque. Okay, so you can linearize the robot equations as well. So the linearized robot equations, so we define delta Q to be Q minus QE. So QE is everything straight up. Delta Q dot, and then this is 0. Delta Q double dot, and then, so we just differentiate. And then the linearized robot equations are this. The C drops out. You have the gradient of the gravity term. And then we get a linear state model by doing delta X, delta Q, delta Q dot, and then delta X dot. It's going to be delta Q dot, delta Q double dot. Okay. We'll call that the first component of X and the second component of X. So this is dx1. And then we have to solve for Q double dot. Okay. So we never like to do inverses, so we use the backslash command. And then we've got minus this is delta x1, and then plus gamma. And when this is all said and done, whoops. This is delta x2, This is 0, 2 by 2 identity, delta x1, delta x2. There's a A21. So these are 2 by 2 zero matrices. And the matrix A21 is the D of Q inverse times minus dg dq qe. And then B will be 0, 2 by 1. And then it works out to be d of QE backslash times gamma. And there it is. So it's a fairly simple linear system. So identity 2 by 2, 0, 2 by 2, 0, 2 by 2. And you've got a 2 by 2 matrix here. There it is. And then this is a column vector, and it's got zeros in the first part, and then it's got not zeros in the second part. So you can derive it either way. You can derive it either way. You can rewrite the robot equations as a first order model in the same states. But what we'll recommend you do in the project, and it's laid out that way, is that we linearize the robot equations. And to do that, you just evaluate the mass inertia matrix at a point, and then you got to take the Jacobian of the gravitational vector term in the robot equation. So you linearize that nonlinear function about the equilibrium point, just like we did everything else. And that's it. And you get the model, and then once you've got the linear models, then you get transfer functions. Then you get your PD controller. And then you add in the precompensator. And you will have a beautiful balancing controller for the, well, you'll do it for the ball bot. So the book does everything for the Segway, and you do it for the ball bot. And at the very end of the project, you take the controller that you've computed, so take the controller that you've computed with the precompensator added to it over here, with the precompensator, and you replace this linear model with the actual nonlinear differential equations of the robot, okay? So you have to take your linear controller and make the real nonlinear system balance and control its speed. So it's pretty amazing, but it's all laid out, and you're going to have to read chapter 10, the second half of chapter 10. Okay, so read through it, and then look through the project, and you'll see where you need to go back and just get a little bit more information. Yeah. Oops. Where I linearize the robot equations? Yeah. Mm-hmm. Yeah, that's where we stopped. So you'll linearize the robot equations, compute a transfer function, design a PD controller. It won't work, just like we did here. You'll design a precompensator. It'll then work, okay? And continue on. So what we're going to do on Monday is go through this process for the segue. But those who want to work on the project 3 over the weekend, for example, you're set up. The first part, you're doing the Lagrangian dynamics. You know how to do that. The second part, you're calculating some transfer functions, and the code is set up so it's not very arduous for you, okay? This third project is meant to be shorter than project 2 and project 1. It's the shortest of all of the projects because we're at the end of the term. On the other hand, it's the most intellectually challenging of all the projects because you're going from a nonlinear differential equation to a linear model to a transfer function, designing controllers, and then implementing them back on the nonlinear model. So it's intellectually challenging, but it's really emulating the complete design cycle that you would do as a control engineer. And it's, when you're done, you have a controller that you can take to Rob 311. Have you balanced your robot yet in Rob 311?
I'm not in the
Oh, I thought you were. Okay, you are. You two are. Have you balanced your robot?
It's balanced, but the controller is still like, if we add the controller function, it's not balanced.
Yeah. So your PD controller is not good because you don't have a precompensator in there, okay? You tuned those gains and it kept getting this wild oscillation. Precompensator, okay? So you guys have seen it on the real robot, I guess. You don't have a simulation model to work with, do you? No, that's hard. At least in the project, it's code. Code doesn't break. Code doesn't go running and hitting the wall and pieces falling off of it, okay? So code is much easier. But you'll be in better shape for Rob 311. So if you guys may want to get a head start, and if you get stuck, you can, you know, ask questions over in office hours. We'll make them private and get you guys going so that you can have a Rob 311 robot that balances. That would be cool. Okay? Yeah. Very good. So we're done for today, and then we don't have any new material, but we're going to go into more details on the segue so that you can have more practice. So if you get partway on project 3 and you get stuck, we'll get you over that hump